Hello, Science 9. We are getting close to the end of this unit on electricity, but we got a pretty big lesson that's actually all just really great applications of electricity. It's about electricity in your home, information about percent efficiency and other really good stuff. But before we get into that, this is a bit of review, but I'm curious to see if you remember. So are circuits in the home connected in series or parallel? Yes, it is in parallel. And the reason why it's connected this way is if it wasn't, then you would have to have every single device on in your house in order for it to work. In series, there is only one pathway for the electricity to go through. So if you disconnect or turn off a device, everything turns off or is disconnected. So it has to be in parallel. So each device has its own branch in the circuit, as I'm sure you'll remember from the topic when we talked about series and parallel. So let's get into this a bit. We're going to first talk about some power generation stuff. Electric current must get to your house from power plants in order for you to use it. And that happens through a variety of power lines. I'm sure you've seen different kinds of power lines. Like, for example, when you drive beside Suffield, you see those massive, huge power lines. The reason why they're so huge is because they're long distance and they're having a very, very high voltage. Like tens of thousands or maybe even 100,000 volts, really high. And that's because higher voltage is more efficient for transmitting electrical energy. And I'm getting ahead of myself, but you know that there's different kinds of power lines involved. There's other components too that we need to talk about, shown a little bit with this diagram. This is more about the power plant itself, but then we have from the power lines a transformer going to our transmission lines. So let's talk about what a transformer is. Transformers are very closely related to kind of what you've already learned about with induction of current when it comes to generators. It's a similar kind of device. Transformers are essentially two sets of coiled wires around an iron core that's a circular iron core or a closed loop. These cores are not electrically connected. The reason why it's iron is because iron is better, of course, at strengthening a magnetic field, as you saw in the lab and as we talked about before. So essentially what happens is alternating current, so current that's changing and going up and down as seen in this diagram here, alternating current going through the primary coil. So I have a primary coil where it winds around, winds around, winds around here. As alternating current goes through there, it causes a changing magnetic field. Essentially, this is an electromagnet, okay, because I have current going through a wire. Well, because that current is constantly changing, it's causing a constant change in the magnetic field. Well, we know that when we have a constant change in a magnetic field around a wire, that induces a current in the wire. So that's where the secondary coil comes in. In the secondary coil, I have on the same iron core, circular closed loop iron core, I have a secondary coil that feels the changes in the magnetic field from the primary coil. And so it induces a current. Now the current it induces will change in characteristics based on how many turns of the coil it has and so on. But it can either increase the voltage and lower the current, which is a step up transformer, so it's upping the voltage, or it can have an effect where it lowers the voltage and ups the current, which is a step down transformer because it's lowering the voltage. But essentially, this the ratio of wraps in the two sets of coils will determine what the output voltage and current will be. But it's just two sets of coils around a closed iron core. Again, those two coils are not actually connected directly. Okay, they're not connected by a wire, but it all works again on this amazing induction, the induction of current due to a changing magnetic field, just as we saw in generators. The difference with a generator is that we instead had permanent magnets and then movement that was causing that induction to take place. So transformers play a role at the power plant in that they step up the voltage. So electricity produced from the power plant is fed into a device called a step-up transformer, and it makes it so that the voltage is incredibly high for transmission. So it's a high voltage, but a lower current. I want you to think about a crowded hallway. When you have a crowded hallway, it's hard to move, right? You have a lot of resistance to movement. Well, a crowded hallway would be like a high current. You have a lot of electrons moving. So the higher the current, the more the resistance is going to be through the hallway, through the conductor. Well, if we have a higher voltage and a lower current, we have less people in the hallway, in my analogy, or less electrons moving through the power line, but those electrons have a higher energy. So we still have the same power, the same, ability to do things, but it's different in that it transmits better and I lose less energy to friction. So high voltage, the reason why we have that happen from the power plant is so that it travels better. It's better transmission through power lines. Once the electricity gets close to your house, it goes through what's called a step-down transformer. These are smaller, and you might see them on power lines and stuff. Like, for example, this is actually a step-down transformer on a power line, and that gets it ready for going to the home. It will lower it to the normal 240 or 120 volts that you use in your house. You actually need 240 for like your clothes dryer. So normally you have 240 volt service as well as possibly 120 volt service also. So you have that going through your house, normally through power lines that are in the ground. But that is a step down transformer because it's lowering the voltage that comes from the power line, which will be higher for transmission, to a lower voltage that can be used in your house. When I was a kid, I actually thought that those were, in my mind, buckets of acid that would dump on people if they tried to climb the power line. I was afraid of a lot of things as a child. Anyways, moving forward, I never climbed any power lines though, so win thinking that one. Buildings have power meters on the outside. They're mounted to the wall. They've changed over the years. So we used to have these ones on the left. They've now all been replaced by these smart meters on the right that actually give you a value here instead of using these dials that move around, which is really nice because those dials were confusing to read and they had to be manually checked by people that would come and take a look at your power meter on your house once every month or few months or whatever to see how your power actually turned out. But now we have these smart meters. And these smart meters are really neat because they actually transmit wirelessly, like through cell phone networks, the information to a central hub for your power company. So anyways, you have these power meters on the outside wall. It records the total electrical energy supplied to devices that are operating in the house. I remember also as a kid, man, I keep on talking about being a kid and you're probably thinking I was the strangest child. And if you're thinking that, you probably aren't wrong. I remember turning off every single device in my house to try to see how slow I could make that dial turn. Still kept on going though because of things like always on stuff like the furnace or whatever that's taking power and needs that to run. After the meter, electricity goes to the service panel, which contains the main circuit breaker. You're going to have the main circuit breaker that actually is kind of like a master switch for the whole house. Okay, and that main circuit breaker will have some kind of current limit that will cause it to trip the breaker if it goes past that. Circuit breakers are essentially just fuses that limit the current going into a device or a home, as high current can obviously be a safety hazard for things like fire or for electrocution. So the idea of a circuit breaker is, for example, if someone is getting an electric shock, it will cut off, because of the high current going through the person, it will cut off the current to make sure that that person stays safe. So the same reason for the fancy plugs you find in bathrooms and kitchens that have a circuit breaker actually built into it as well to make sure that with all the water around, if there is a short, it shuts off. Fuses are slightly different than breakers. What a fuse is a really thin wire, and that wire actually burns and the connection breaks if the current gets too high. But because fuses have to be replaced and it's a pain, this has been replaced over time with breakers that instead can just be flipped. Like you can just flip the switch to turn the circuit back on if it does actually end up tripping the breaker. I know that in my house, for example, we have one area that tends to always trip, and actually it's my office. And it trips when I have a heater on, a space heater, because it's a little bit cold in the office sometimes during winter. And like if a vacuum or something else that's high current is going and plugged in the same area. There are circuit breakers in the service panel as well for each electrical branch in your home. And each branch will supply a few plugs, lights, or devices. Sometimes it'll be like kind of 1 or 2 rooms. You'll have a breaker that's devoted just for certain devices, like for example, your clothes dryer and your oven and that sort of thing. Like really high current devices will have their own special breaker. And then you have breakers that, will be, for example, for kitchen outlets or whatever else. These branches and all devices and plugs are connected in parallel. So they're all separate. They all have separate electrons or current going through them, unlike series. So just a reminder, if you don't remember what parallel means, if I have my power supply right here, and I'm going to actually draw this as like the AC, like this power supply. If I have this going to different loads, right, there's different branches. So here's one branch, there's a load I'm drawing as a resistor, and then there will be another branch for another room or area or device with another branch. So if this one goes, right, if this one is off, then this one still goes. So that's the neat thing about it. Okay, let's talk a little bit about electrical cables in your house. I think this is important as general information to know and understand and important for safety. There are 3 wires that go into most of your outlets, and they have not what you normally would think of in terms of different, symbols. The main thing is that white is actually kind of what would be the positive of a normal power supply, but it's white instead of red. We call that the neutral wire. Don't let that confuse you though. That doesn't mean it's not dangerous. That wire is live, and if you do touch that wire, it can, if you're grounded, cause you issues and can electrocute you. Black is your negative. That's where electrons are coming out of, high energy electrons, and that's the hot wire is what we call that. That's also live. Do not touch that. And under no conditions touch the black wire and the ground wire, or the black wire and the white wire at the same time, because if you do, you are going to receive a very nasty shock that could kill you. I'm going to right away say this: never, ever, and I mean at this age, never, ever play with your outlets, period. But as you get older and you're dealing with different stuff in your house, and maybe you have to replace something like an outlet or a switch, turn off the breaker in that area. Check the outlet first with the device like a lamp or something to make sure that it's not connected, and double and triple check before you touch the wires. I myself, somebody who actually knows a fair amount of electricity, have gone very close to shocking myself. For example, I was renovating a bathroom at one point and discovered that, I forget if it was a light or the exhaust fan, but one thing was not connected to the breaker that I thought it was, and it was live when I thought it was not. And I'm very lucky that when I touched it, I think both wires at the same time, so that with the same like piece of metal, so that it traveled through the metal instead of traveling through me. But it did cause a spark, and I think it flew the screwdriver or something when I did that. It's scary stuff. So you got to be careful. Always make sure that your breaker is turned off for that area before you even considering touching stuff. And then ground is copper or green, depending. So either it's just bare copper and doesn't have any insulation around it, or it has a green insulation around the wire, so like the rubber coating, plastic coating. And that's ground. It's not live. It is no electricity running through it, and it's basically your safety. So the idea is if a short circuit occurs, everything just goes straight through to the ground instead of it charging the object itself. If the ground wasn't there, and let's say your white wire came off and it was something that had metal in it, that metal could then give you a shock. So the idea of the ground is that it's always providing a pathway for electrons to go if something goes wrong, if something fails. The ground wire reduces shock hazards by giving a pathway for excess or leak charge to travel. Normal plugs and devices use a voltage of 120 volts with a few exceptions, like for example your clothes dryer, which is running on 240 volts typically. Okay, summary. I feel like I have to say this again. Don't touch your outlets or switches and stuff. Don't play with electricity in your home. There used to be this character called Louis the Lightning Bug. I'm going to see if I can find a video and put it up here. Okay, it's fun. It's retro. You'll enjoy it. I used to have a shirt that had a glow-in-the-dark Louis the Lightning Bug, and I loved it. All right, moving forward. So this is actually a picture of the wires from the side of an outlet, and you can see that I have the black and the white wires connected. So I have black on the other side of the outlet and white here, right? So black is your negative, that's the hot wire. White is your neutral wire. And so when you plug a device in, it's actually connecting the black, it goes through the device and it comes back to the other side, to the white, and that's how it gets power. And then this down here is your neutral. So that's the copper wire that you're seeing here. Okay, so this is all neutral wires that are going to, or not neutral, sorry, ground, not neutral. These are all your ground wires that are, again, there for safety and very good to have. But that's how your outlet is wired and how it works. So now you don't have to see it yourself. If you look inside of a calculator or any type of a computery type device, you're going to see a ton of stuff that you just don't recognize. It's all very fascinating and all very tiny and normally deals with a very small voltage that's going through it, which allows it to be tiny, tiny pieces. If it was a high voltage or a high current, it would not actually be able to work very well because it would burn out the device. But let's talk a little bit about transistors. We're actually seeing a bunch of things here. These are little tiny capacitors. Capacitors build up charge on one side, and then when it gets to a certain point, that charge goes through. Resistors, you know, that's a resistor right there. It looks very similar to a capacitor. And then we have computer chips, and computer chips contain a ton of teeny tiny transistors, which are embedded in there. Don't want to go through transistor kind of layers and stuff, but it's neat tech, and they're getting thinner and smaller all the time. But what transistors are is they're like switches that aren't mechanical. So unlike a normal switch that you flip up or down, it's not like that. It instead is a switch that activates based on an input of current or how high the current is. And it's turned on or off by an electrical signal. This is the whole reason why we have computers and computation. If it weren't for transistors, the next best thing that was used before was these, what do you call them? Vacuum tubes? I feel like I'm getting that wrong. That you would find in like tube amps and stuff. Transistors are of course incredibly small in comparison and have allowed for everything that has to do with computers and calculators, and they're incredible. When these transistors work together, they are able to do simple, and then eventually, as we get more and more and more complex operations, as we get into computer chips and get thousands and millions of transistors working together in these complex arrangements. So just know that transistors, which are made out of semiconducting materials, silicon is the base, and then you have arsenic and gallium mixed in there as well, and phosphorus. But silicon being in there acts as basically a switch, a solid state switch, so it doesn't have any mechanical parts, and that switch is turned either on or off from electrical signals. Okay, moving forward. We're going to talk about some formulas, and this has to do again with devices and kind of what we use in the house. You've probably seen before different power ratings. Maybe you're into like audio stuff, so you know power of speakers. Maybe you've looked at different powers for devices around your house, like air conditioners or ovens or heaters or whatever. I mean, even actually this heater that I have right here, I wish I could show this to you easily, but it actually has a power rating. Oh, I'm gonna lift it. No, you won't be able to see it. Never mind. It has a power rating on two switches on the side where I can turn on different amounts of power as it goes through. I think I showed you that with the resistance the other day for some of you with my ohm meter. But power ratings are all over in devices that we use in the house. So we're gonna learn how to calculate power, and we're gonna use two formulas that involve power, but we're gonna start with this one, which is kind of the base of how power works. Power is equal to the energy delivered to the device divided by the time over which that occurs. Now this time is going to be in seconds and energy is in joules. So given that I'm taking energy in joules and dividing it by time in seconds, that means that power is a joule per second. But we actually give us a special unit, which we call a watt, capital W, because it's named after James Watt of steam engine fame. But watt is a joule per second. And actually even horsepower is a power measurement. It's just a different unit. And I forget what it is. It's 800 and something watts is a horsepower, I think. I should look that up because I think it's interesting. Whoa, typing in the wrong place. Horsepower watts is 745.7. I was close with 800. 745.7 watts is equal to 1 mechanical horsepower. So that also is a power, but we're not going to deal with horsepower at all in this class. We're just going to deal with watts. And again, that's equal to energy divided by time. So let's take a look at a quick example for this and see if we can figure it out. Let's say we have a light bulb that has 204 joules of energy supplied to it in 2.4 seconds. What is the power of the light bulb? So we're going to go through the full problem solving process that we did before with Ohm's law. We have our energy, which is equal to 204 joules. We have a time equal to 2.4 seconds. And I'm looking for the power of this light bulb. So power is equal to energy divided by time. So my power is equal to 204 joules divided by 2.4 seconds. So remember that in your calculator, we don't care about the units. All we're doing is dividing those two numbers to get an answer. So we're going to take 204 and divide it by 2.4. I'll do this right here. 204 divided by 2.4, and I get an answer of 85. So that means I have a power equal to 85 watts. So I have 85 watts there. Sorry, you're going to see all my messy tabs. 85 watts of power for that light bulb. Okay, so what this means, and actually I need to change this value because I think I originally meant for it to come out to 60 watts, and instead the calculation is 85. But, oh no, that's fine. Let's just consider it as being a 60 watt light bulb. Sorry, let me erase that. So if I have a 60 watt light bulb, not the 85 from the last example, but if I have a 60 watt light bulb, that means that it converts 60 joules of electrical energy to heat and light every second. In other words, 60 joules of energy goes into the light bulb each second and gets converted to other forms of energy. So that's, a definition of a watt. Another way that we can calculate power is using current and voltage using this formula, which we use quite often. P is equal to I times V, where I is current in amps and V is voltage in volts. And that also will get me power in watts. The reason why this works, if you care, is that if you remember, an amp is equal to a coulomb per second, and a volt is equal to a joule per coulomb. So if you take a look at these two things together, right, current in amps times volts or voltage, then I have coulombs canceling out, and I end up with joules per second, which is essentially watts. Don't worry about that if that confused you for units, but I think it's just always interesting to show how this works mathematically when it comes to units. But this formula we are going to now try to use to find out different things, and you will of course have this on your formula sheet as the last one as well, to answer questions when they come up. Now, P equals IV can be converted to two different forms as well if I want to solve for current, which is of course the I. Then if I wanted to solve for that, I'd start out with the original formula, P equals IV. I need to get rid of V. So the way that I get rid of V so that I can get I alone on this side is I divide both sides by voltage. That will cancel out voltage over here, and I end up with current is equal to power divided by voltage. If I want to find voltage, which is V, then it's going to be a very similar process, but instead I'm doing it to I. I divide both sides by I cancels out, and I end up with voltage is equal to power divided by current. So these formulas I'm going to have to be able to use as well. You won't be given these formulas because you can get it from this formula. So as long as you know this formula, you can get to these two. Just remember that power will always be on top. This will always stay on top. So when I'm finding current or voltage, power will be on top of the other thing that I'm not solving for. So let's try one example. Let's say we have a 200 watt speaker, which is a very powerful speaker, and it's powered by a 12 volt power supply, and I want to know what is the current that's running through that speaker. So I would start out by writing my power is equal to 200 watts. And I have a voltage equal to 12 volts. And I am looking for my current. So P is equal to IV. I want to solve for I, so I'm going to divide both sides by V. Gets rid of it. So I have current is equal to power divided by voltage. So I have a 200 watt speaker. Remember to always put your units in whenever you have a number. No number can have or can be without units, because then I don't know what it is. 200 watts divided by 12 volts. In fact, talking about horsepower kind of showed how I need to define the units when I give a number, because otherwise you don't know if you're talking watts or horsepower. In fact, if you want to make your vehicle when you're driving sound really impressive, tell them the power in watts. It's going to sound awesome. Times 750 your horsepower, boom, there's your watts. Okay, so I have an answer of 16.7 amps. So all I did is I put 200 divided by 12 into my calculator, 200 divided by 12, and I got 16.7 amps there. Let's try one more. What voltage can be supplied to a 50 watt power supply if it has a max current of 2.80 amps? So now I'm doing a little bit of a different calculation. I am now finding voltage instead. So I have 50 watts for my power. I have a current, an I, equal to 2.80 amps. And I want to know what my voltage is. That's my question mark. So P is equal to IV. If I want to solve for V, I'm going to divide both sides by I to get V alone. And now I have voltage is equal to power divided by current. So I have 50 watts divided by 2.80 amps. So 50 watts divided by 2.80 amps. Let's now try the calculation out and see how that goes. So I have 50 divided by 2.80. And I get an answer of 17.9. So 17.9 volts. A little bit of rounding here because I'm going to cut it off at the 10th, might as well. The number after the 10th, after the 8, is a 5, so that rounds up to a 9. So 17.9 volts is the voltage that is coming out of that power supply, or you could say 18 volts. That's great. Probably better to just say 18. But of course, I'm not picky with how many decimal places you use for these. But yeah, that's the answer right there.